Welcome back. Today we are exploring the tools that make calculus actually visible, graphing calculators and modern computer algebra systems. These devices, they are absolutely incredibly powerful for solving complex problems, but there is a pretty massive catch. If you don't use them carefully, they can, and for sure will, lie to you. As mathematician James Stewart famously warns, only through calculus can we be sure we have seen everything a graph has to offer. So today we're going to set you up as a mathematical detective. We're going to uncover the truth hiding right behind the pixels and learn exactly how to avoid what we call the visual trap.
Okay, let's dive into this. Like we just heard from James Stewart, we really can't just trust a screen blindly. I mean, we naturally want to, right? You type in a function, you hit graph, and you just assume that that beautiful curve lighting up your screen is the absolute truth. But blind trust in calculators, that leads directly right into that visual trap. See, machines don't actually understand math. They just follow rigid programming. Relying on actual mathematical reasoning, specifically through calculus, is literally essential to making sure you aren't being completely deceived by a faulty visualization.
To understand why machines lie to us, we first have to understand how they actually see the world. A graphing device doesn't see the whole infinite expanse of the Cartesian plane. Not at all. It only sees a tiny, restricted peephole. This peephole is called the viewing rectangle. You can think of it as a strict mathematical box. It's the set of points x, y, where x ranges from a minimum a to a maximum b, and y ranges from a minimum c to a maximum d. Everything outside that strict boundary, it's completely invisible to the machine. It simply doesn't exist in that moment. And choosing this window, well, it is an art form. It's exactly like taking a photograph. If your window is too small, you completely miss the end behavior of the graph. You literally can't see where the function is heading as x approaches infinity. But on the flip side, if your window is too massive, you zoom out so far that the small, crucial, intricate details right in the middle completely disappear. Think about a simple function like f of x equals x squared plus 3. The absolute lowest value this graph will ever hit is y equals 3. So if you casually set your viewing rectangle's y values between -2 and +2, you're going to get a completely blank screen. The machine isn't broken, you're just pointing your camera at the wrong part of the sky.
And this brilliantly illustrates the danger of a poorly chosen window. Take a look at a rapidly oscillating function like f of x equals sine 50x. If you plot this in a standard viewing window, say -10 to 10, the output just looks like a solid block of color or this distorted, blocky mess. Why does this happen? Well, because the oscillations are so incredibly fast. By giving the calculator a wide window, it's desperately attempting to cram hundreds of rapid peaks and valleys into just a few dozen pixels. It physically cannot display that density. To see the clear, distinct oscillations, you'd actually need to shrink your X window way down to something tiny, like -0.25 to +0.25.
To understand why it outputs that garbage, we have to look at the machine's fatal bug. When you hit graph, the calculator isn't actually doing fluid, continuous calculus. It just operates in two very rigid steps. Step 1, it plots a set of equally spaced points across the x-axis of your chosen viewing rectangle. Step 2, it blindly connects each point to the preceding one with a straight line segment. That's literally all it does. So, with a rapid sine wave, the machine might sample a point at the bottom of a valley, skip completely over the next peak because it didn't sample there, and plot its next point in another valley. When it connects those dots, it misses the peaks and valleys entirely, creating a completely false, jagged line.
This mechanical dot connecting creates another famous pitfall, the extraneous line trap. Let's look at the rational function y equals 1 divided by the quantity 1 minus x. If you remember your algebra, you know this function is undefined when x equals 1, because, well, that creates a 0 in the denominator. There is a gaping hole right there. But remember our calculator's algorithm, it plots a point just to the left of x equals 1, where the graph is shooting way up to positive infinity. Then it plots a point just to the right of x equals 1, where the graph is shooting way down to negative infinity. And what does it do next? It blindly connects them. It draws a steep, almost vertical line right across the gap, making it look like that line is part of the graph. It is absolutely not. The machine is just connecting dots across a gap.
So, how do we catch these lies? Let's investigate a new suspect. Consider the cubic function f of x equals x cubed minus 150x. If you plug this into a standard viewing window, say -5 to +5 on both axes, it deceptively appears as a nearly blank screen, or really just a boring, nearly vertical straight line. It looks like absolutely nothing is happening. If you didn't know better, you'd probably write down that this is just a straight, steep line and move right on to the next problem, completely unaware of the massive features hiding just out of frame.
But as a mathematical detective, you know better. By dramatically zooming out to a completely new viewing rectangle, let's set our x values from -20 to 20 and our y values all the way from -1000 to +1000, we finally uncover the truth. The shape completely transforms. It's not a straight line at all. It is this beautiful, sweeping curve with a distinct hidden local maximum and a local minimum. But seriously, how on earth were we supposed to just guess to set our y window all the way to 1000?
So the crucial point here is, we don't guess. We use calculus. Calculus actually helps us predict where the action is. Before we even touch the calculator, we can use algebra and calculus to calculate the true domain and range of the function. Even better, by calculating the derivative of the function, which we'll be learning a lot more about later, and solving for exactly where that derivative equals 0, we can mathematically pinpoint the exact coordinates of every single peak and valley. Instead of randomly zooming in and out and just hoping we spot something, calculus mathematically dictates the perfect viewing rectangle. We know exactly where the action is, so we never have to blindly guess.
And now here is your challenge. It's time to test your new detective skills. If you graph f of x equals x to the 4th power minus 16x squared plus 20, which window actually shows you all the turning points of this W-shaped curve? Is it window A, ranging from -3 to 3 on the x-axis and -5 to 25 on the y? Or is it window B, ranging from -5 to 5 on x and -50 to 50 on y? Open up your own graphing app, try it out, and tell us which one works and why in the comments. I can't wait to see your reasoning. Thanks for joining me for this explainer, and be sure to tune in next time when we dive into the explosive, fast-paced world of exponential functions.